What I want to cover now is analysis of variance, or an ANOVA, using the R core package. Okay? Again, so just to reiterate, if we're actually interested in asking questions about whether one treatment is different from another, and we care about the relationship of those two treatments, we're going to be testing a fixed effect model. If, on the other hand, we're more interested in the distribution of the values and estimating the variance associated with those effects in our model, then we're going to be on this random effect track. So we have to be able to articulate a model for our analysis. And in this data set, we have two ways of looking at that. Okay? We have the full data set, where we can look at the stand count in July relative to plant genotype, inoculation, the interaction of those, the year, the rep within year, and the year by genotype effect. Okay? We could potentially, the year by genotype effect. So, rep within year is basically the within environment variation, right? Genotype by inoculation method is going to be telling us whether some genotypes are affected by the inoculation method or not. Okay? Another way of looking at this same problem is to use the new data 2 set of data, which only contains data from the inoculated trials. In which case we drop out the inoculation term, and we're really just addressing whether genotypes are different under inoculation, because that's all we have here. Here, the genotype term is really confounded by the fact that we've got data for both inoculation and non-inoculated here, right? Okay, so there's two different ways of doing it, but either way serves a purpose. Okay? And then we're using a linear model or regression to perform this analysis of variance. And so this is the syntax that we will use in the core package. So we're using an object, and I call it fit1. LM is the linear model. Y is equal to, and then we articulate the model. We don't have to specify error. Okay? Just as in SAS, you wouldn't specify error. Okay? And so this is what I mean from the previous section when I said before you even do your experiment, you need to know what your model is. Okay? All right. So it's going to be easier if you go ahead and attach the data to do this. All right? And remember when we used the structure data 1 command and we looked at the data, we saw that year and rep were treated as integers. Okay? If we treat them as integers, the math gets a little funny, because year is coded as 2014 and 2015. And so the math is going to assume that there is a difference of 1 between the two treatments, 2014 and 2015. And that's obviously not the case, right? We just mean these as factors, right? The same with rep, right? Rep 4 is not 4 times rep 1. It's just a numerical code for the factor. So we're going to create two new variables, year in capitals and rep in capitals, where we say treat year as a factor and assign it here. Same with rep. Okay? All right. And so then we can go ahead and write out our model. Okay, submit that line of code, and then we use the statement ANOVA fit1, and it's going to return the analysis of variance table. Okay? And so what do we get? So first of all, you should review the degrees of freedom and make sure that makes sense, right? So we know we have 8 genotypes, so the degrees of freedom is 7. That makes sense. 2 inoculation methods, makes sense, 2 years, so it's all making sense, right? You can refer to the Macintosh paper to make sure that the degrees of freedom are calculated as you think they should be. All right. We're getting the sums of squares, the mean squares, the f value, and then a p value. This number 2.2 times e to the minus 16 shows up over and over and over again in R. It's because this is the smallest number that can be stored before the storage kicks over. The failure to account for that storage limit has caused airplane crashes. If you don't believe me, look it up. All right? So, highly significant genotypic differences, highly significant inoculation method differences, significant year-to-year differences, and a genotype by inoculation method interaction. Okay? All of this, but no year by... Okay, so that even though we wrote this as a nested effect, the math is the same, so it shows up as an interaction effect. So no within year variation that's significant, and no genotype by year variation that's significant. Okay, so all of this is pointing to the fact that it matters if the plants were inoculated or not, and that there are genetic differences that appear to be emergent. Okay? Again, so we can just interpret that relative, okay, so relative to our model. All right? And again, I'm just pointing out that we're getting the degrees of freedom, sums of squares, mean squares, the f value, and the p value. So what we're going to do now is we're going to simplify our lives. We're going to go ahead and detach that file, data 1, and we're going to attach the new data file that we corrected. Again, we have to make sure that we define year and rep as factors, and we have a new simplified model. Right? Okay, so again, we've got now we can drop out inoculation in any term with inoculation. We have genotype year, rep within year, and genotype by year. Okay? Right? Perform the analysis of variance. And again, what you're seeing here is that genotype differences are highly significant, but the other terms are not. Using analysis of variance, we set the object to AOV1, and again, this is just a name. In order to extract the analysis of variance table, with the AOV function, we use the summary command. And you can see that the table is structured exactly as the one in the previous slide, which was extracted from a linear model. Now I want to deviate just a little bit from R and talk about analysis of variance in general. So from the Macintosh paper, you can put together a table of expected mean squares for different experimental designs. And I've laid out that table here for our experiment. In this case, treatment is equal to genotype. Okay? And the expected mean squares are outlined under this column here. So the expected mean squares can be used to help us determine the proper f-test. So for example, if we want to test our treatment effect, our f-test is going to be the mean squares for treatment divided by the mean squares for error. We isolate that term. Okay? So this is one reason why it's important to understand what the expected mean squares are. There's more that we can draw out of the ANOVA though. So if we understand what the expected mean squares are, we can set those equal to the observed mean squares in order to estimate the variance due to each factor in our experiment. And so keep in mind that the variance due to treatment is in fact the genetic variance. We may want to actually solve for that term. So in order to get an estimate of genetic variance, we can set the observed mean squares for treatment equal to the expected mean squares here. We have two variables, variance due to treatment and variance due to error. So we need two equations to solve that. So we set the observed mean squares for error equal to the expected mean squares, and then we can subtract those two equations. Okay? It's simple algebra. And the math is worked out here. Right? And so you can see that we can come up with an we can come up with an estimate of our genetic variance by simply knowing the mean squares for error and the mean squares for genetic treatment. All right. So remember when we looked at the distribution of data, we thought that there might be a reason to transform the data. Right? Okay. So in this model, what I've done is I've simply transformed the stand counts in June. I added 1 to everything simply because you cannot take the log of 0. So if there's something where nothing grew, you're going to get a 0. Okay, so I just simply added 1, a constant, and then took the log. Okay. And we can simply repeat the analysis, and again we see the genotype is still significant. All right. Now, there is a function called plot that we can use to examine the distribution of data and residuals to see which analysis, either the raw data or the transformed data, better fit the assumptions of the analysis of variance. And so when you exercise that command, what you're going to see is that you have to click through a series of windows. So we could modify the code so that all 4 of them would be displayed, but for simplicity, we're not introducing that to you yet. So if you run this line of code, you then have to click and go window through window. You're going to get 4 different windows. I've chosen just to show the normal QQ plots. Okay, if the data and the residuals are fitting the expectations, they're going to line up on this dotted line. And so what you can see is that even the transformed data doesn't quite fit, but it's a better fit than the untransformed data. Okay? So just a way of analyzing whether the transformation better fits the assumptions of the analysis of variance or not.